Okay, so we've had a brief look at graphing piecewise functions. I might post a couple of links for you for some more help on those because they can get a little tricky, especially if some of you I know have already been struggling to just graph a regular function. So to graph a piecewise function, you have to be able to graph a regular transformation and then recognize which bits you need. So it's going to get a little tricky. Make sure you put in some good practice on this one. We've got two other things to look at in our lesson today. We've got to look at just a little bit of review of finding zeros, thinking about factoring, and also a small review of working with complex numbers. So let's help you with these a little. So this is actually on your homework. So I'm helping you with your homework. So pause your video and try it on your own before you let me do all the work for you. So what do we mean by the zeros of a function? The zeros are the values of x that make the function equal 0. So what we're looking for here is the value of our function equals 0, and we've got to solve this equation. I want to see an equation. Please do not skip writing, oops, that should be a minus. Do not skip writing 0 equals. If you're not showing me an equation, then you've got nothing to solve. Write out your work precisely. It's important. So this is quadratic. How do we solve something that's quadratic? We've got two choices. We factor it and then know that one of our factors must equal 0, or we can use a quadratic formula. Factoring is much easier if you can do it. So let's actually see if we can factor this. This should be easy. Pause your video, try it on your own. And let's go over this. X squared must come from x times x, 8. That could come from 1 times 8 or 2 times 4. Which pair of those have got a difference of 7? Well, it's the first pair, isn't it? 1 goes in here, 8 goes in here. One of them must be positive, one must be negative to end up with -8 at the end. If I put the negative here and the positive here, would that be right? Check it. Some of you aren't checking. This gives me plus 1x. That's my inner. My outer here would give me -8x. Put those together and I don't get plus 7x. It matters which way round you put those. Please check. Some of you are not doing that and it's really going to hurt you on your answers and your solutions. And that's often just a first step in a problem. We're going to move on from that. So you've got to get it right. So that was wrong. Haha. Get rid of what I put in there. Oh, stop it. Stop it. Stop. I did that. Let's erase those because those were wrong. Put it the other way around. So this must have been negative and this must have been plus. Check it. -1x plus 8x just does give me 7x. So I now can use what we call the zero product rule. I have a product. I'm multiplying two things together. I'm multiplying this factor by this factor, and the answer is the product. If a product is 0, it only works if this here is 0. If this was another number, we can't solve it yet. Okay? It's only because this equals 0 that we know that one of those factors must equal 0. So either x minus 1 equals 0 or x plus 8 equals 0. I know this is really simple. This is back at Algebra 1, but I know some people never actually got what we were doing there, and it hurts later on if you don't understand that. So solve this, add 1 to both sides. That gives me x equals 1, and this one gives me x equals -8, and those are my zeros for this function. You want to check them. I must admit, even I don't even bother checking things like that. You could put them back in the original and check that 1 squared plus 7 times 1 is 8. Take away 8 and you end up with 0. It works. But, oh, wow, I never even thought of checking that. I won't make you check that. So try this one. Oh, I don't want to try that one. Oh, my goodness. What's that going to be? 0 equals 3 times t squared minus 27. Oh, it looks scary, but it isn't. Look, you've got a GCF. Both those numbers are divisible by 3. So this equals 3 is a factor. Don't just throw it away. Factor it out. 3 times t squared minus 9. And that is the pattern A perfect square minus another perfect square is what we call subtraction. It only works with subtraction. It's difference. Difference of perfect squares. And we're going to use that so often this year. If you have the difference of squares, it comes from what I call, we have lump squared minus blob squared. You get lump minus blob. That was blob squared. So this is square root of blob. Sorry. Lump squared minus blob squared gives you lump minus blob, lump plus blob. Okay, you don't have to remember with lumps and blobs. It makes me happy though. Okay, so we have to solve this now. We still haven't finished. So we've got three things that are being multiplied together here. We've got 3 times factor number 1 there and factor number 2. One of those factors, at least one of them, must equal 0 for our answer to be 0. Does 3 equal 0? No. So that's not a 0 of the function. But t minus 3 could equal 0. And look, we're working with t's here, not x's. I just didn't even notice that. Or our other factor must equal 0. So this gives us 2 zeros. That gives me t equals 3. And this one gives me t equals minus 3. And if you wanted to, you could be very lazy with those two. I don't mind you writing this at all. T equals plus or minus 3. That's a perfectly acceptable way to write your answer. Okay. Some people find it clearer if it's written like that, but that's fine. Now the question asks for zeros. How would you rewrite that if the question had said, tell me your x-intercepts? Well, x-intercepts are a point on a graph. They don't just have an x value, they have a y value. So if I wanted x-intercepts, this would be x is 1, y is 0. This would be x is -8, y is 0. You're doing exactly the same math, but read the question to get the format of your answer correct. X-intercepts are points, zeros are a value that x equals. Moving on. You can do those ones yourself. Oh, number 10. I'm not going to do it for you. Try that one. That one's a really, really good one. Nice, juicy one if you ever go at factoring. Okay, complex numbers. When my daughter's now at college, I probably shouldn't talk about it, but she had an imaginary friend, and her imaginary friend used to tell her jokes, and she'd start laughing. Now, I know you probably thought that imaginary friends are for toddlers and for math teachers to give you problems that you don't really want to solve. They made up math. They made up things that don't exist just to make you do math problems. Well, when I got to college, I studied engineering, and I actually found out that imaginary numbers are the most incredibly useful thing. They were developed by this mad mathematician who did make up something that didn't exist, I don't know, about 300 or 400 years ago. But when people started working with electricity, so that's 150 years ago, and they developed alternating current, the only way that an electrical engineer is going to be able to work with alternating current electricity and design circuits that don't blow up when you turn your lights on in your home is by using complex numbers in math. They're brilliant. They solve so many things in engineering. Anyway, so complex numbers have got a real part and an imaginary part, okay? And the imaginary part is based with I, where I squared equals -1. So I is the square root of -1. And as we were just working with domain last week, we know that that doesn't really exist. But I've just told you it's very useful. So if I squared equals -1, you tell me, what does I cubed equal? You work this out. What does I to the power 4 equal? What does I to the power 5 equal? What does I to the power 6 equal? Let's have a look. Well, I cubed is I times I times I. And we know that I squared, so that's the same as I squared times I. So this is, and I squared is -1 times I. And what would I to the power 4 be? Well, that's like I squared times I squared, 4 of them, yeah? 2 there and 2 there. So that's like -1 times -1, which we hopefully know by now is +1. And what would I to the power 5 be? It would be that times I. So it'd be just I. And I to the power 6 would be this times another I. So it'd be I times I, which would be -1. And you'll see a pattern that develops. It's just interesting to play with that pattern. So now I want you to simplify these. It's just FOIL. All you're doing is FOIL. 2 plus I times 4 plus 3I. You just FOIL it. 2 times 4 is 8. How about putting an equal sign to say it's equal to what's on the line above? F outer. Now I always do the outer and the inner together, and I make them look like a happy smile and a silly nose. 2 times 3I. So it's plus 2 times plus 3I gives me plus 6I. That's my outer. And my inner gives me plus I times 4. So that's plus 4I. And then the last plus I times plus 3I gives me I times I squared. And there's a 3 there. So we've got plus 3I squared. Now this is why I do my outer and my inner like that. It's this nose and my mouth, because those two normally combine together. So we have 8 plus 6i's plus 4i's gives me plus 10i. And then I've got plus 3i squared. Now don't forget I squared is minus 1. So what I've got there is plus 3 times negative 1. Now obviously you can do some of this stuff in your head and don't have to write out quite all this work. 3 times negative 1 is minus 3. So 8 subtract 3, that gives me 5. If I combine this is now a real number. Got rid of I squared. I got rid of the imaginary part. So here I've got 8. Take away 3 is 5 plus my imaginary part. Now, you can write the I first or the 10 first. It really doesn't make that much difference. Now, this one is a interesting. No, that's not the one that's very interesting, but never mind. Okay, I'm not going to do all your homework for you. If you need the answers, they're on the key. It will be published and you can have a look at it later. Have a wonderful, wonderful day. How do I stop my video? I never know how to stop this thing.